Alright, how's it going everybody? Today we're going to be talking about a few things, but we're going to start off first with how temperature is related to the kinetic energy of an atom. So let's talk about a few things. Let's talk about kinetic molecular theory. What is kinetic molecular theory?
That just means that all of matter is made up of tiny, tiny, tiny particles. So you've heard us talk about mass, how everything is made up of stuff. Well, that's really all that this means. Everything is made up of stuff. All objects are made up of stuff. They have matter. And matter is made up of tiny particles. So
what do those tiny particles do? Are they just kind of stagnant? Do they stay there in the same place, or do they move around?
They're always moving around. Even solid objects don't look like they're moving. Those tiny particles inside of them are moving all the time.
Okay, so do some move faster than others?
Yeah. And you can tell when things feel hot. That means that if things have a high temperature, that means the molecules inside of them are moving very, very quickly. In liquids, the particles in liquids tend to move faster than the particles in solids, and so on.
Okay. Let's talk about thermal energy. Thermal energy is the overall kinetic energy of particles that make up an object. So when temperature is increased, you increase the speed of the collisions, and therefore you increase its thermal energy. So it's kind of like when you boil water. You're going to speed up. The hotter it gets, the hotter the liquid gets, the faster those little molecules are going to go. And that's going to increase the temperature, and which makes it start to boil. So, what is temperature?
Temperature, then, is a measure of the kinetic energy inside of the system. As the objects heat up, as the liquid heats up, for example, in the case of boiling water, those molecules are moving around faster. The kinetic energy increases. Potential energy decreases. Kinetic energy increases. And that's what temperature is a measure of.
Okay, so we have a picture here on the screen that says you have one right here where this is all low movement stuff. These aren't moving very fast. You can see by the trails that they leave, they're not very big. But if you look on this side over here, on this side they have the long tails, which means that they're moving at a much faster rate of speed. Therefore, makes it a higher temperature. Okay, so what is the correlation between temperature and pressure?
Well, as temperature increases, so does pressure, because the particles are moving more quickly. It's kind of like if you trapped air inside of a balloon. The particles in the air are moving around all the time, hitting the sides of that balloon. If they were moving around faster, then the balloon would probably want to blow up a lot bigger, have a lot more pressure inside of it.
Okay.
From hot to cold. From hot to cold, heat transfer goes from hot to cold, from hot to cold, from hot to cold, from hot to cold, from hot to cold. Heat transfer goes from hot to cold, from hot to cold, from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat, it always goes from hot to cold. You'll always remember this, kiddies, even when you're getting old. When you go out to dinner, you want food that is super real hot. But if you wait too long to eat, oh, you'll be so sad with what you got. See what happens, it's really easy. The food is sitting out and touching the air. The heat from your food's not disappearing, it's being transferred to the air. Cause heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Now summertime and you're at the pool, jumping off the high dive. Once you hit that cool water, it feels like you're frozen alive. See what happens, it's really simple. Your body has a warmer temperature, cause once you touch that cooler water, it's taking your heat energy for sure. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Thermometer is a tool we use to measure heat energy. It measures particles' movement. They're moving endlessly. When molecules gain heat energy, they move around faster. The liquid expands and the temp goes up on the thermometer. Cause heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Grab some different objects sitting in your room at home. Some feel cooler, while others are warmer, but they have the same temperature. So the reason is that some objects conduct energy better than others, meaning it takes energy easily. We call these things conductors. The objects that warmer, we call these insulators. They don't conduct energy that well, so I'll see y'all later. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold.
Now, when we reach thermal equilibrium, what is thermal equilibrium?
It's the state in which two bodies are in physical contact with each other, and they have identical temperatures.
Okay, so let's say if I have a cup of coffee and I have just a regular cup of water, and I have the coffee is hot and the water is room temperature. The thermal energy, the thermal equilibrium between that is when you put those together is going to be the combination and what the level actually levels out to, what the temperature levels out between the two, and it's always going to take the difference between the hot, and the difference of the cold. It's never going to get any hotter, and it's never going to get any colder unless there is a reaction, a chemical reaction.
Like a balance being reached between the two
Right.
temperatures.
So what do we measure, or what do we use to measure temperature?
We use thermometers. Everyone's seen one, right?
So if we look at a thermometer and we use a thermometer, we're not actually measuring the temperature of the water or whatever we're using to measure. We're actually measuring the temperature of the thermometer. So if I stick a thermometer into a glass of coffee, I'm not measuring how hot the coffee is. I'm measuring how hot the coffee makes the thermometer. So therefore, your body has a greater thermal energy than the thermometer. So the coffee had a greater thermal energy than the thermometer, which actually made it the temperature rise. So we talk about temperature scales. We have Celsius, we have Kelvin, and we have Fahrenheit. And Celsius is used all over the world. When we use Kelvin, who uses Kelvin?
Really just scientists, like astronauts and scientists at NASA. It's just kind of it's the scientific units for temperature based on absolute zero, which means 0 Kelvin. So like in outer space, typically, that's where we would find 0 Kelvin.
Right. What 0 Kelvin is absolute zero. It's whenever all molecules actually stop moving.
Yeah.
They freeze it in place. Now, we actually haven't been able to get there. We haven't been able to replicate absolute zero energy, but we've gotten actually pretty close. And then we have Fahrenheit, in which what we use and what y'all use in an everyday thing. So, it's 80 degrees outside, so it's going to be not extremely hot, but still pretty warm. So let's talk about heat for a minute. Heat is the thermal energy that flows between objects. That's what heat is. So you have two pictures here. You have one picture on the left where you can see the energy flowing outwards, and that's how you know that it's hot, because the energy is escaping and flowing into your hands, while you can see the temperature is actually all the way up there. While cooler objects, the heat from your hands would be flowing into the object, which causes a lower temperature.
Wait, so what's the difference between heat and temperature then?
What is temperature? Tell me temperature.
Temperature is a measure of kinetic energy.
Okay, kinetic energy.
Mm-hmm.
All
In
right.
the system, yeah.
So we have these pictures here. Let me go ahead and go to the next one. So which direction is thermal energy usually transferred?
From the hot object to the cold object.
Okay, and we have a picture here representing that right now. You have your hot object here, and it's flowing outwards to the cold objects. Again, right here, so it's the same thing. Heat always transfers from hot to cold, and heat does not rise. So, we have that common the term where heat rises, hot air rises. Well, it's not the hot air itself; it's actually the air. Now, the heat is trapped within the air, which actually makes it rise, but it's not heat that itself rises. Okay, so what is the difference between temperature and heat? All objects have the same temperature because all objects have some energy. Now, heat is the energy being transferred because of the temperature difference. If there is no difference, there is no heat. Now, let's talk a little bit about thermal expansion. What happens to solids, liquids, and gases when you increase their thermal?
They expand, like hot air expands.
A lot of you, when you go driving, if you've gone driving and you go over a bridge, you hear that split in the bridge right here, ta-tum, underneath your tires. Well, what that is a gap that is made for thermal expansion. Because if there's, as things heat up, they expand. And if they didn't have that thermal expansion, see how you show it right here, how some of these gaps are right here? If they didn't have that thermal expansion, well then there'd be no room for it to go and would end up actually looking somewhat like this. The cracks in the sidewalk, how they deform because they didn't have that extra room to go, any extra room to grow because of the thermal expansion. So let's talk about heat and work. Heat produces work by causing expansion. Now, how would we get a positive expansion?
Well, when you have a change in volume, when something is growing, moving away from its original size, that's a positive expansion. And then compression is a negative expansion. It's shrinking from its original size.
Okay, so work is only done if the volume changes, right?
Right. Remember, whenever we were talking about work before, we said that work can only happen if there's a displacement. Well, this volume change counts as that displacement.
All right, we're going to talk about one last thing. We're going to talk about thermodynamics. Now, what is thermodynamics?
Well, thermodynamics literally means moving heat. It's a relationship between heat and work, heat and movement, and a change in displacement. We can use heat to do work because of thermodynamics, because heat causes movement.
Okay, so let's talk about the first law of thermodynamics, and that is that it restates the law of conservation of energy. Now, we've heard this term before, law of conservation of energy, and that means, again, that energy can't be created or destroyed. It can only change form. So we're going to demonstrate a cylinder of gas in the system and pistons, kind of like how an automobile would use, and how it would use that to create work. So we have this here. Now, when the piston moves up, when this piston goes up, that means this internal gas right here is actually expanding. So when this gas expands, then you are going to have actually a negative energy, or a negative, because it is decompressing, therefore you have negative. And when it actually presses down, it's compressing against the gas. When this goes down, you would have a positive. It would be a positive work. Sorry. Okay.
All right. So then the heat creates movement, and then the heat extracted from the gas is what's causing the work. That's what that Q is. It's the difference between the expansion and the contraction, the work being done.
Okay, and the internal energy will increase if heat is added, or decrease if work is done. Let's go ahead and take a look at the next one. This is just another ad on this. Let's take a look at these. And we'll talk about the second law of thermodynamics. The entropy of the universe always increases. Now, what does that mean?
Well, you can kind of look at it as reality entering into the system. In a perfect world, all the energy that we put into the system would be converted into mechanical work. Unfortunately, that really doesn't happen in the real world. Some of the energy escapes as heat or whatever, and that's because of entropy. Everything tends toward chaos. Disorder always enters into a system.
Okay. So we have entropy happening to the ice cube. The ice cube, which is a crystal structure with minimal entropy and maximum order. Well, whenever over time, it's going to melt. It's going to melt into a puddle of water where there's actually no structure, and that's going to be maximum entropy and minimal order. Just like you said, chaos. If there's no set structure for it to be a part of.
Yeah, molecules want to move around more than they already are.
Okay, so let's go ahead and finish this off. It says adding heat to a kinetic system, or adding heat to a system increases kinetic energy and entropy, and removing heat from the system does what?
It decreases the kinetic energy and entropy.
All right, well that's it for us, guys. We'll see y'all next time. Thanks a lot for listening.